Ahmed. I think everybody knows Ahmed very well, and he's a master's student.
My mic offered.
And he completed his undergrad studies at University of Illinois, and he continued with his master's studies in our research group. And apparently he fell in love with Illinois winters, and I'm not sure what his next move going to be, but he's going to be with us at least for this winter. And the title of his presentation is Development of Effective Testing Protocols to Ensure Performance of Mixes with High Amounts of Recycled Content. So this is a presentation derived from the findings of the ICT project R27128 presented at TRB. And without further ado, I'm welcoming Ahmed to make his presentation.
So, can you hear me? Okay. I'll just present this presentation. Okay. Good afternoon, everyone. My name is Ahmad Khatib. Today I'll be presenting, as Professor Ozer mentioned, testing protocol to ensure performance of asphalt mixtures with high amounts of recycled content. This is an ICT project headed by Professor Ahmad Al-Qadi, Professor Ozer, and Professor Lambros. It's a joint collaboration between ICT and the Aerospace Department. And then I also recognize my colleagues, Tamim Khan and Puneet Singhvi. So I guess the way I structured the presentation is just initially a very brief discussion of the motivation for the project. I want to talk about the increasing use of RAP and RAS in the state of Illinois and kind of how this motivated the study. So from the years 2012 to 2013, as you can see, there's a 43% increase in Illinois recycled tonnage in the use of recycled content in the state of Illinois, basically. And then from the years 2012 to 2013, there was a 221% increase in the usage of RAS in the state of Illinois. RAS, just for comprehensiveness, is just as recycled asphalt shingles, and whenever I say RAP, I'm referring to recycled asphalt pavements. These are the two primary materials of interest for this project, and very widely used in the state of Illinois, as you can see here. Furthermore, in the year 2013, 821,000 tons of RAP and RAS were used, and this comprises about 19% of the total asphalt mixtures produced. So it's very clear, the point is very clearly made that the usage of RAP and RAS is significantly increasing throughout the United States, but also in the state of Illinois, which motivates the need to understand how this usage of recycled content affects the material behavior and properties. And so the project goals and overview for the study, we're attempting to identify a testing protocol that can basically characterize these materials with the addition of recycled content. And we want to identify very critical engineering properties of these asphalt mixtures. The final product is not limited to mixtures that have recycled content. So whatever our team is developing can be used for any asphalt mixture in order to screen its performance. But the motivation for the study is the use of recycled content. And the primary distresses are fatigue and thermal cracking. So we know that basically with the addition of recycled content, it's typically agreed upon that adding recycled content will embrittle your material, will make it more brittle, which makes thermal cracking and fatigue primary concerns. You wouldn't expect, rutting to be a primary concern if your material or your mixture is becoming more brittle. And so this is the reason these two distresses or failure modes are the primary areas of focus. And so when we think about developing this test to accurately screen these asphalt mixtures, there's a set of criteria that we must follow. And the first of them is basically we have to have significant and meaningful spread in our test output. So regardless of how scientifically sound our research is or how theoretically backed and proven our final product is, if it doesn't do a good job of basically distinguishing between mixtures, which we know are very different, both in terms of mix design and also performance in the field. If our test does not do us an acceptable job of distinguishing between these mixtures and doesn't give us significant spread in our data, then it's not very useful. Second, we want to make sure that whatever product we deliver to the Illinois DOT is feasible, as practical, and is repeatable. And so it's very difficult to propose a modification to testing that is expensive and difficult to perform in the field and very complex and just time consuming, whatever product we deliver has to be cost effective, practical, simple, and easy to fabricate the specimens, easy to run the test, easy to analyze the results. Additionally, we want appropriate correlation to independent tests and engineering intuition. I don't, if I'm expecting as an engineer with experience a mixture to behave very poorly, I need my test or my specification that I develop to tell me that basically, and I need to be able to correlate my results from this specific test method to other independent tests that can verify the validity of this test method. And then finally, correlation to field performance, right? This is the ultimate objective. Whatever we put out, you want to make sure that, the results that you're predicting in lab, the performance you're predicting in lab is correlated to field performance. Because at the end of the day, that's really all we care about. How is the mixture performing in the field? So with these test method selection criteria in mind, we move forward. And so today I'll be discussing basically the development of this test. We have developed a test. A flexibility index that we believe is meeting these criteria. There's room for obviously improvement and further development of the test, but my intention today is to discuss the results of our work and to present the flexibility index to you. And so our research approach, how are we kind of approaching this project? We have over, I would say, about 30 plus mixtures that we've analyzed in our lab, and there are three primary sources of material for this project. The first is our plant mixtures, which are sampled on site in asphalt plants. The second source is laboratory produced mixtures. So my colleagues, Puneet and Tamim and I have been developing, and Jose have been developing mixtures in the lab. Have been developing mix designs basically with varying amounts of RAP and RAS, so you can control exactly the mix design properties and see the effect of these different variables on performance. And then field cores that we've extracted from the field and we've tested in lab. And we've selected the mixtures that we've used in this study strategically. So we wanted as diverse as possible of a spectrum of properties. So you can see here from just this table we have, our asphalt binders range from PG 5228 to PG 7622. We have a nominal maximum aggregate size of 4.75 to 19. We have N30 to N90 end design values. We have, all kinds of recycled content in our mixtures. We have RAP, RAS, recycled concrete, and steel slag. And we have asphalt binder replacement value, percentages of 0 to 60%. So we get pretty high up there with the asphalt binder replacement percentages. RAP content ranges from 0 to 53%, and our RAS content ranges from 0 to 8.5%. So we've really pushed the envelope with how different we can make our mixtures to make sure that whatever flexibility or whatever criteria we develop is kind of robust enough to analyze all kinds of different mixtures. And so, having said this, I present to you the semicircular bending test. This is, mostly everyone's probably heard about this test. This test is basically a three-point bending, a very simple three-point bending test. It's a fracture test, right? And the specimens are produced from the superpave gyratory compaction cylinders. And what you do basically is you compact your cylinder in the superpave gyratory compactor. You remove the top and bottom portions of the cylinder or the pill, and then you basically extract two 50-millimeter thick slices from the center of the pill, half them, and then notch basically the base of each half, and that results in the SCB, the semicircular bending beam test, which you can see in the figure to the top right. And then so it's a very simple test specimen fabrication process, and the most important thing is that we can test these specimens under a very simple pneumatic load frame. So you can see in the picture to the bottom right of the slide is the Humboldt load frame. And basically, this is a very simple. This is actually the load frame used for the TSR test. So we've modified the fixture for the standard TSR test. Very simple, cost-effective modification, and you can run the test essentially on the Humboldt load frame at a very cheap cost, a very simple modification. And this is the final objective of the project, to be able to deliver the test that runs on the Humboldt load frame properly. And in terms of repeatability, we've seen very, very good repeatability values, typically below 15% coefficient of variance. actually typically below 10% coefficient of variance. So I mean, we've kind of really narrowed down or we've minimized the variability in this test. So our results are significantly more repeatable than when we started. And so a little bit of discussion as to what the SCB test criteria actually is. So we've taken the classic SCB fracture energy test, which is run at minus 12 degrees Celsius, and is controlled by the horizontal displacement at the bottom of the specimen. You can kind of see the clip gauge kind of stuck to the bottom of the specimen there. We've taken that test from minus 12 degrees Celsius, and we've run it at the classic SCB test conditions. But we've kind of shifted the temperature to 25 degrees Celsius, and we've shifted the displacement control from the bottom horizontal displacement of the specimen, which we call the CMOD. We've shifted that to basically the LVDT. So the test is now controlled by the linear variable displacement transducer, shown to the right of the figure shown here. And it's basically just a vertical displacement that controls the displacement rate of the test. So after a screening of different displacement rates, we've tried maybe displacement rates ranging from 6.25 to 50 millimeters per minute. We've selected the optimal displacement rate of 50 millimeters per minute. And this provides the best variability, the best distinction, and the best results basically from the test. And so the parameters that we calculate from this test are as follows. You have the fracture energy, which is typically what's calculated in the classic low temperature SCB test. You have the critical displacement value, W sub 1, and I'll discuss all of these on the next slide. You have the peak load, which is simply just the maximum load that your specimen experiences during the test. You have the displacement at the peak load, so whatever basically displacement your vertical transducer is experiencing at the peak load. And then you have the slope at the inflection point, the first inflection point past the peak load. And we call that M, basically. So what am I talking about here, right? So you can see here, so what typically happens is you get a low displacement curve, and you would calculate the area under this low displacement curve, which would result in the work of fracture done. Then you normalize this value by the ligament area, and that gives you the fracture energy. So very simply, the fracture energy is just the area under this low displacement curve normalized by some specimen dimensions. Additionally, the other parameters we extract are the peak load, which can be seen there, then the slope at the inflection point. So past the peak load, I'm looking for my first inflection point in that kind of post-peak softening portion of the curve, and I calculate the slope of the line fit through the first inflection point, and that gives me my value M, my slope value. Then you can see the critical displacement value, which is basically where that line fit through the inflection point intersects the x-axis. And then finally, you can see the opening at peak load, which is simply just the LVDT displacement at the peak load. So these are the parameters of interest. And what's typically been used in the classic SCB test is simply just the fracture energy. So you can see that it's just the area under the curve, and that's what's been used for screening mixtures for low temperature cracking potential. And so we went ahead and we ran the test under the minus 12 degrees Celsius SCB horizontal displacement controlled condition. And the following are the results. So we have, a variety of mixtures ranging from 0% asphalt binder replacement to, you can see here, 60% asphalt binder replacement. And the data spread, the basically range of fracture energy values extracted from these tests is approximately 250 joules per meter squared. So this is a very limited spread of data. These are very different mixtures. You can tell simply by looking at the asphalt binder replacement values. Some of them have no recycled content whatsoever. Some of them were replacing 60% of the binder with recycled content. And the spread in our data is not too significant. You can see here that it's very limited. It's a value of 250 joules per meter squared, which is not too different from actually the experimental error that we experience. And so the bottom right corner of the slide shows the low displacement curves for these low temperature tests. So you can see that for about 5 or so laboratory produced mixes that we've developed from 0% RAS to 7% RAS with varying PG grade binders, the low displacement curve is basically identical. These mixes are not performing any differently under low temperature conditions. And they're very different mixtures. You're going from 0% RAS to 7% RAS, which is about 30% asphalt binder replacement. And so this is the issue with the low temperature testing condition, that we don't have significant spread in our data. And we need significant spread if you remember the test selection criteria. Because I know that these mixtures are performing differently in the field, and their mixed design properties are very, very different. So with this issue identified, we shifted to basically 25 degrees Celsius. And these are the results for 25 degrees Celsius. Keep in mind now that the displacement is controlled by the vertical displacement of the SCB specimen. So 25 degrees Celsius, vertical displacement controlled, and same mixtures basically. Now you see that the data spread has shifted from 250 joules per meter squared to 1,271 joules per meter squared. So there's a significant data spread basically in these mixtures tested at 25 degrees Celsius. And so this was kind of a promising result that tells us basically that this temperature is better distinguishing between these mixtures under the SCB testing condition. And again, these tests were run at the selected 50 millimeters per minute that I discussed earlier. And so this slide will show you basically the spread in data, will better visualize the spread in data between the low temperature testing condition and the 25 degrees testing condition. You can see that at low temperature, at minus 12 degrees Celsius, there's not, again, significant spread in the data, or there's limited spread in the data, whereas at 25 degrees Celsius, 50 millimeters per minute, we see much better spread in our data, which again leads us to pursue this temperature and this loading displacement rate for further development of the index. And so we move on to the shortcoming that we have basically with the 25 degrees Celsius. So we've kind of addressed the shortcoming in the low temperature testing condition. Now we're faced with another shortcoming, and that is basically that the fracture energy is not a sufficient criteria to distinguish between mixes on its own. So I have here low displacement curves for two very different mixtures. Again, this is so the black curve is our N90 lab-produced mixture, and it's a control mixture. There's no recycled content whatsoever. It's completely virgin. The N90 lab mix design 30% ABR is a mixture with 7% RAS. So you would expect these mixtures to perform differently. I mean, nobody would argue that they would have similar performance. And you can see from the low displacement curve that they do behave differently, right? One mixture, the red curve, which correlates or corresponds to the 30% ABR, is significantly more brittle. It's less ductile and is displaying a higher strength or peak load value. Where the control mix is displaying a more ductile kind of lower peak load, lower strength value. But if I look at the fracture energy, which is, again, the criteria typically used to screen mixtures or grade mixtures, if I look at the fracture energy of these two curves, the black curve displays a fracture energy of 1790 joules per meter squared. And the red curve displays a fracture energy of 1780 joules per meter squared. So I've selected these two curves, these two mixtures, to show that basically, even at 25 degrees Celsius at 50 millimeters per minute, I have two very different mixtures with identically or with practically identical fracture energy values. And if our objective is to basically distinguish between mixtures, then the fracture energy is not sufficient on its own. And so to the bottom left, you can see basically the progression of laboratory mixes that we've developed. So there's about 6 or so laboratory mixes that we've developed in our ICT facility, and you can see that we start off with a control mixture of N90 0% recycled content, PG grade of 70 minus 22, and then we begin to basically deteriorate the mixture with the addition of RAS. So we keep adding basically, well, first we take it to a softer binder grade, right? So the N90 0% 6422, and we add 10% RAS. Then we add 20% RAS. Then we add 30% RAS, and then we vary the binder. So essentially what's happening is a deterioration of the mixture as you take it more to the brittle end of the performance spectrum. And so as you're increasing the ABR, you are decreasing the virgin binder in the process. And VMA and total AC content were kept constant. So one of the issues that we potentially could face when testing at intermediate temperature, at this temperature at 25 degrees Celsius, is kind of complications with the fracture energy values that we are extracting. So there are two primary areas of concern when testing at 25 degrees Celsius. Sorry, excuse me. The first area of concern is basically complications at the loading head, which is signified by the 1 here, and also the roller supports. So you want to make sure that there isn't any significant deformation at any of these points. Otherwise, the results that you're getting, the displacement results you're getting, are kind of tainted. I'm trying to move this out of the way, but it's not working. Okay. Okay. Additionally, you have complications at the point signified by the box that says 2 basically, and the other box that says 2, which are basically the far field additions to the fractional energy. So the objective is basically to make sure that testing at 25 degrees Celsius is not introducing any spurious energy dissipation to your results, because this can result in a calculation of basically inaccurate or inflated fractional energy values. And so with this motivation, basically, we have a two-pronged approach to addressing these potential concerns. And the first prong of that approach is the finite element simulations, or the FEM work, which my colleague Ziad is doing. And the second prong of this approach is the DIC, or digital image correlation. So the DIC work, if I can move to the next slide. We have basically a set of two cameras. One of them is a very high resolution, low speed camera. The other is a relatively low resolution, high speed camera. And this allows us to capture full field deformation measurements of our specimens as we test them. And so you can see the setup there. And this is being tested at 25 degrees Celsius, again, room temperature. We basically just record the deformations on the specimen for the duration of the test. And we can calculate things like strain fields from this that we couldn't regularly see with our naked eye. Thank you. That we couldn't regularly see with the naked eye. And so what kind of things can we do basically with this DIC that we couldn't, again, do with just the raw data that we extract from the test? We can look at the effective rate and temperature on fracture. We can do things like look at the aggregate microstructure and see basically, we can quantify the effective aggregate microstructure on fractional energy results or displacement results. We can look at the effective recycled material content being added to the mixture in a way that we wouldn't be able to see basically with just, again, the raw data extracted from the test. And then additionally, we can address the aforementioned issue of the spurious inelastic displacement, which again is not related to the fracture but could be added at 25 degrees Celsius. And then finally, we can extract viscoelastic parameters such as the J integral, the stress intensity factors, and most importantly perhaps the fracture process zone. We can do all these things with these cameras that we wouldn't be able to do basically with just the data extracted from the test or our own visual assessment of the specimen as it's being tested. And so I wanted to discuss basically the fracture process zone exploration that we've been doing with these cameras. And so here's basically a very cool looking video of the specimen being displaced and captured with the cameras. And so you can see we painted the specimen, sorry, with a kind of so we start off with a white base and we speckle it with black dots. And what the software is doing is basically tracking the movement of these black speckles on the specimen in order to calculate full deformation fields. And so from this full deformation field that we can calculate, the strain field essentially, we can look at the fracture process zone. And so this is a specimen tested at 25 degrees Celsius, 50 millimeters per minute. And here, my colleague, again, this work is primarily done by the aerospace department, which is collaborating with us. So my colleague Berenjet is basically calculating the strain fields in the specimen as the test is progressing. So you can see that. Okay, I wanted to just show it again. So she's calculating the strain fields as the test is progressing. And you can see the development of the fracture process zone there. And so what we've done is we've looked at the fracture process zone for different scenarios, different testing scenarios. So we first started out with testing basically the same mixtures, our 0% RAS at minus 12 degrees Celsius, the classic SCB testing condition that I mentioned earlier, and at 25 degrees Celsius, 50 millimeters per minute. And you can see the difference in the fracture process zone. So at minus 12 degrees Celsius, at the lower temperature, the fracture process zone is kind of limited to the crack tip region. It's not really extending much past the crack tip. But at 25 degrees Celsius, there's a kind of diffusion of the fracture process zone further out into the specimen, and you can see that it's much more prominent in regions further away from the crack tip. And so we can conclude from this that basically the effect of shifting the temperature from -12 to 25 C is a diffusion of the fracture process zone. And we hypothesized that basically in the field, what's happening is something similar to the 25 degrees Celsius testing condition, where the fracture process zone is much more diffused throughout, the bulk regions of the material, of the asphalt pavement. Then we took our control mix, which is 0% RAS, and we tested basically its kind of deteriorated derivative, right, which is the 7% RAS, and it was tested at both -12 degrees Celsius and 25 degrees Celsius. And so you can see that, again, we can make a comparison now, an apples-to-apples comparison between the control mix and the 30% ABR or 7% RAS mix at both -12 degrees Celsius and at 25 degrees Celsius. And so you can see that what happens is, as you add recycled content to the mixture, as you add the 7% RAS, you are essentially embrittling the material. This is without a doubt. And this is proven by basically the localization of the fracture process zone. You can see here that as compared to the -12 degrees Celsius, the fracture process, as compared to the control mix, the 7% RAS mix displays a much more localized fracture process zone. And this is true for both -12 degrees Celsius and 25 degrees Celsius. And so, again, going back to the development of the flexibility index, having begun to address all of these potential complications that come from 25 degrees Celsius testing temperature, we proceeded to the development of a flexibility index. And I should mention, by the way, that if I can go back here, the FEM work that we're doing has preliminarily shown us that basically these spurious inelastic energies that we are concerned with comprise about less than 10% of the total fracture energy values that we're getting. And so we've kind of chosen to, the work is still ongoing, and we'll further prove this, but we feel very confident basically that the spurious inelastic energy contributions are not too significant. 10% is within the experimental error of our own experiments, which is why we're not considering this value in our tests. And so moving on to the developed flexibility index, what we basically did is we took a step back and we looked at basically the critical parameters that I discussed earlier, and we said, how can we basically characterize different materials, and how can we distinguish between different materials? And the result that we came up with was a purely geometrical. We found the answer to be in the geometrical properties of the load displacement curve. So the fracture energy is, again, just a geometrical characteristic of the load displacement curve. But there are other parameters that you can extract that I mentioned earlier, such as the peak load, or the slope at the inflection point, or even the critical displacements. And so what we found to be most effective and most in line with engineering intuition, again, preliminary prediction of field performance, and also independent tests, was this combination of the fracture energy and the slope. So this slope here, the slope of the line fit through the first inflection point past the peak load. And so let's talk about the structure of this index a little bit. So basically, the higher the slope of the load displacement curve, so a material that gives me a higher slope of this line, of the line fit to the point, the first inflection point past the peak load, the higher that slope, the more brittle my material is, right? And so the higher my slope, the more I can kind of penalize the mixture for behaving in a much more embrittled fashion. The fracture energy we included because the fracture energy still tells us something about the behavior of the material. And so then we added this factor of A, which basically just makes the results of the flexibility index look nice. This can be a factor of 1,000 that you divide by, or 100, or whatever basically is needed to make the results look nice. So this is the proposed flexibility index, just simply the fracture energy divided by the post-peak slope of the line fit to the first inflection point past the peak load. And we found that this index, again, as I mentioned, correlates to other independent tests, which I'll mention later. So let's go back to the example that I showed earlier of the two load displacement curves. of the two very different materials that were displaying basically identical fractional energy values. So you had 1780 joules per meter squared and 1790 joules per meter squared. When we basically run these numbers through the flexibility index expression that we proposed, you can see the huge distinction between the two mixtures. So the red curve, or the more brittle curve, or we can agree the lower performing curve in terms of low temperature fracture resistance, displays a flexibility index value of 6.2. Whereas the black curve, or the softer, more ductile curve, of the lab mix with 0% RAS displays a flexibility index of 11.3 for its basically fracture performance. So you can see that basically the black curve is displaying a significantly higher flexibility index than the red curve. And so the distinction is then made. So then these two mixtures are distinguished between basically using the flexibility index, which was not done before using the fracture energy. And so then we looked at the performance of all of our laboratory mixtures. And if you remember that the lab mixes I discussed earlier, basically we started out with a very, very good parent mixture of an N90 0% RAS, PG70 minus 22. This is, by the way, polymer modified. Then we basically bumped the binder down to a softer binder, and then we added basically different amounts of RAS. We're basically making the mixture worse and worse. And so if we look at the fracture energy results and compare them to the flexibility index values that we calculated for these mixtures, we can see some very important differences. First, the fracture energy seems to make a jump basically from this N90 0% PG64 minus 22 mixture to the N90 10% PG64 minus 22 mixture. So all things are held constant between these two mixtures except for the addition of basically 10% asphalt binder replacement, which is 2.5% RAS. So if I'm using my so we can all agree that the addition of this 10% asphalt binder replacement, or 2.5% RAS, would result in a lower resistance, but in a lower resistance to potential basically thermal cracking. So if I'm using fracture energy as my distinguishing criteria, it's misleading, right? Because I'm getting here a higher value for the fracture energy for the mixture that I would expect, and that's proven basically to behave more poorly under low temperature cracking conditions. And so this is kind of a very concerning observation that we've made using the fracture energy as the criteria. However, if I use the flexibility index we've developed, I can see a much more logical, much more intuitive relationship between these mixtures. And what basically happens is, as I go from the N90 0% to the N90, PG70 minus 22 to the 64 minus 22, as I'm softening the binder, I basically get a bump down in the flexibility index. The reason for this is because the 70 minus 22 is polymer modified. So it's just a better binder all around. It displays higher peak loads. It displays higher ductility. And so I get a bump down basically in the flexibility index. As I add 10% asphalt binder replacement, or 2.5% RAS, I get a further decrease in the flexibility index. Then I basically use a softer binder, a PG58 minus 28, and then I add 20% ABR, or 5% RAS, and I get a bump up, which was resulting from the softer binder. Then as I further deteriorate the mixture and add an additional 10% asphalt binder replacement, resulting in a 30% total asphalt binder replacement value, I get a further decrease. And then finally, when I use basically the worst possible combination that I could of all these parameters, so 30% ABR, 7% RAS, and then PG70 minus 22, I get a further decrease. So the flexibility index trends are intuitive, right? And they make sense. You would expect the two extremes of the spectrum to be which two mixes, right? You'd be expecting the N90 0% 70 minus 22 to be the best performer, and the N90 30 70 minus 22 to be the worst performer. And so this is a further validation of the flexibility index. And so with this in mind, we've proposed preliminary thresholds to be used for basically distinguishing between different mixtures after running the results through the flexibility index. So the following slide is just a presentation of all of our results from our plant mixtures. And so we have a lot of mixtures basically plotted on this figure. And what you can see here is as you move to the right, so on my x-axis I've got the flexibility index values. We've tested all these mixtures, run them through the flexibility index we proposed, and basically looked at where they fall on this spectrum. as I move further towards the right, I would expect my mixture to be a better performing mixture. And I move further, as I move further towards the left, I would expect basically degradation or deterioration in the performance of the mixture. So if we look at some basically examples, I can see here that P12, for example, so this guy, P12 is again closer to the right side of the spectrum. P12 is a 26% ABR mixture with a 70-28 binder. It's only 8% RAP, 5% RAS. If I look at, for example, P10, which is so well performing that it's actually off of the flexibility index value for that is past 10. We just put it right there for demonstration purposes, basically. But it's much higher than 10. It's flexibility index value. And P10 is basically a mixture with 25% ABR, a very soft 58-28 binder. Then as I move towards the left of the figure, I'm approaching basically mixtures which are not so good in terms of resisting low temperature cracking. And so let's, for example, look at P9. So P9 is a mixture with 59% ABR, resulting from the combination of 42% RAP and 6% RAS. So that's a lot of asphalt binder replacement. And the AC content for this mixture is 5.6, right? So I can see that this mixture falls on the left end, basically, of the spectrum towards the poorer performing mixture side. And so as you move towards the left, you have increasing cracking potential. What we've proposed, basically, is to subdivide this spectrum up into 3 different figures. And again, these thresholds will be further fine-tuned as our database of mixtures increases. So as we can better correlate to field performance and field cores and field surveying data, we can better refine and fine-tune these thresholds to result in more accurate, basically, prediction of performance. So then we looked at our field cores. I mentioned that we had a bunch of field cores from all of the IDOT districts. And we did the same exercise, basically. We plotted them. X-axis is flexibility index. And what you can see here is, again, as you move towards the left of the curve, you have increasing cracking potential. And I want to discuss two special, basically, field core mixtures that we tested. So the F24 and the F23. So we actually have field surveying data or performance evaluation data from the field for all these mixtures. And the F24 mixture displayed very poor field performance, while the F23 mixture displayed very, very good, excellent field performance. And so we can kind of begin to see our flexibility index being validated by, again, field performance. And so I mentioned the three categories. So you have type 1, type 2, and type 3. So essentially what would happen is if your mixture falls in the type 3 region, which is all the way to the left of the flexibility index spectrum, then you would basically reject the mixture due to high early cracking potential, and you would redesign. You would make modifications to the mixture and then rerun the test, basically, and see if this mixture still falls in the type 3 region. If your mixture falls in the type 2 region, the mixture would be acceptable, but kind of mediocre performing in terms of low temperature cracking resistance. And then the type 1 mixture is the acceptable, excellent performing mixtures, which can be used, which can be used in surface overlays or typical pavement applications. You can see kind of where we aren't considering for per se structural or application variations in these mixtures. So I'm not saying that if you have a road with lower traffic levels, then you would take that into account as you basically decide to pass or fail the mixture. And I mentioned correlation to an independent test. The correlation of our flexibility index test, basically, to an independent test. And so you selected the Texas overlay test for that correlation. Texas overlay was developed by Zhao, and it's a qualitative test. It's conducted at room temperature, 25 degrees Celsius, like our proposed SCB, at a displacement of 0.025 inches and 1 hertz, basically, loading frequency. And recent studies show that there's very good correlation between this test, the Texas overlay test, and field performance. And so what we did is we tested our mixtures under the Texas overlay with the help of IDOT, and we've also tested them under the SCB. And so there are seven primary mixtures included in the study, ranging from 0% RAS to 3.5% RAS, from 0% RAP to 50% RAP, and so very different mixtures. And what we saw here basically is that there is significant, there's pretty decent correlation between the SCB flexibility index values and the TOL cycles to failure. So if I look at the SCB flexibility index values, the highest performing mixtures are, this is kind of cut off here, but you can, the x-axis is the same. So the best performing mixture is basically P7, and then like one of the lowest performing mixtures is P5. And even though there's only 6% ABR in P5, there's something that went wrong basically in the mixing or compaction or basically production of the mix that we don't know. So actually, it's interesting because IDOT's TOL test cycles to failure matched basically ours. So this mix 5 is one of their lowest performing mixtures for a reason that we are not sure of yet. They're conducting forensic studies on this, but one of the lowest performing mixtures and one of our lowest performing mixtures for the mix 5. And then for our best performing mixture, there's a match or correlation basically between their best performing mixture of mixture P7. So the two extremes of these two tests are matched. So good mixtures match and poor performing mixtures match. There wasn't such a great match in the middle region basically between the good and poor performing mixtures. But we can say that the extremes, the very different mixtures are basically identified in both the SCB and the TOL cycles to failure. And so conclusions that we've drawn from this study, the first conclusion is that low temperature fracture testing has very limited data spread. So there's a need for basically an addressing of the shortcoming. You want to make sure that whatever test you're running, again as I mentioned, gives you significant differentiation between different mixtures in the field. Then we switched to 25 degrees Celsius and we decided basically that fracture energy was an insufficient parameter on its own to predict cracking potential because there are complications with misleading fracture energy values. So a mixture that would perform much worse in the field is resulting in higher fracture energy values. And this kind of motivates a need for a practical, sound, and cost-effective testing protocol that would allow us to predict our AC cracking potential. And to address this need, basically, we've modified the SCB test. We've modified how we look at the results from the SCB test. And we basically proposed this new approach of looking at the low displacement curves, extracting critical geometric properties, the fracture energy and the slope of the line fit to the first inflection point past the peak load. And we've developed a flexibility index that has shown significant promise in indicating cracking potential for both field mixtures and has matched engineering intuition. And we've also shown significant correlation to an independent fatigue test, the TOL Texas overlay test. And we were able to match basically the extremes of the performance spectrum. So the excellent mixtures from both tests matched, and the poor performing mixtures from both tests matched. And so with that, I'd like to acknowledge the ICT project technical review panel, my graduate colleagues, the undergraduate researchers, and the ICT engineers. Thank you.
From the online attendees, Josh.
Yes.
I had a question about how you came up with the regions for type 1, type 2, type 3 for the flexibility index. Was it a certain number or like?
So again, so you're referring to these guys, right? Yeah. So these thresholds, as I mentioned, are preliminary, right? And I forgot what you were saying. Are preliminary, and they need to be fine-tuned as we, again, as I said, increase the database of field performance. Where they're coming from now is basically engineering intuition. So engineering intuition coupled with basically kind of just like the mixed design properties of the different mixtures that are being tested. So you would expect, again, a mixture with lots of recycled content, right, with lots of RAS to be a poorer performer in the field. So these are kind of just very, very preliminary thresholds, very open to basically refinement in the future. Yeah. Aaron?
I guess a couple of questions. I'll start out with what I think should be the easiest. But what's the current allowable ABR percentage in Illinois?
I think it's 25%. 20%. I'm sorry, 20%.
Okay, and you guys are going as high as 60, which is good. I mean,
Yeah.
It gives a clearer indication of what's happening. But if you go back to your slide that's actually showing the comparison between the Texas overlay and your SCV at room temperature, I think it was maybe a bit of a bold statement to say that it's properly identifying the extremes when your lowest result from the Texas overlay is coming up as either your second or your third highest flexibility index from your SCV. Your 212 on the Texas overlay.
Right. Well, but if you look at P2 and so P2 and P5, if you compare P2 and P5 results from the Texas overlay, they're not too different. So I mean, I would say that they're kind of in the same performance range. There are some issues. I mean,
they're similar for that test that you're trying to compare it to, but then they're no longer similar for the SCV. I mean, it's a very limited set, so
yeah.
I don't want to be too critical
Sure.
of some of those, but again, might be a fairly bold statement.
I would repeat or maybe emphasize that it's just the extremes that we're comparing. And I mean, there are some issues with the Texas overlay test.
The statistical analysis that you made.
Right. So actually, when we ran this through stats analysis, and basically the categorizations, I'm not showing actually the error bars here, but the categorizations of the different materials for the mixtures for best performing and poor performing did match through statistical analysis. So I mean, like it's for us. I mean, maybe for example, the P2 mixture has a very high error bar, whereas the P5 mixture is very much low variability. I'm talking about the TOL test. So I did run the results through statistical analysis, and the outcome was basically that the two extremes matched. Yeah, I'm not saying the tests are interchangeable or that you can use one to predict the performance of another, but it is a confirmation or an encouragement that basically our test is at least able to basically match the Texas overlay at the extremes.
One of the main points or questions that will probably come up from a lot of people that would watch this presentation would be the concern of shifting the temperature. I think you maybe downplayed it at the beginning, saying, well, we kind of shifted the temperature from -12 to 25.
Yes.
And then when you start looking at your digital image correlation, mm-hmm. it also shows that there is a difference in your region. You know, the dispersion of that fraction,
right,
or that fracture zone.
Mm-hmm.
And then you kind of just jump to saying, so we hypothesize that this is more similar to what's happening in the field. Is there any DIC data from the field that helps support that?
Well, not currently, but that's actually what we're working on right now. Maybe as we speak, we do hypothesize that the field basically fracture process zone is more similar to the 25 degrees Celsius, and we're confirming that with the DIC work currently.
You want to be more than just a leap of faith
sure.
in saying, yeah, well, we assume this is maybe more similar.
Sure.
And I think what maybe would help that is if you had similar ranking in the materials. You know, as you work your way toward a more economical and a more practical test, which is obviously accomplished by running at 25 degrees so that you can do it in your Humboldt load frame as you showed, rather than worrying about an environmental chamber.
Yeah.
Do the rankings of the performance remain similar to that of the test when conducted at -12?
So that assumption would require it would require the assumption that basically low temperature testing conditions are appropriate or like are properly.
You are investigating a temperature dependent viscoelastic material. So
right.
when you're looking at low temperature
failure or fracture, the rate we're using for low temperature is 0.7 millimeters per minute, which is significantly faster than what I would say happens in the field. So it is low temperature, but again, like precisely because this is a viscoelastic material, the rate that you're testing at really matters, as well as the temperature. So just because I'm testing at low temperature doesn't mean that I'm accurately portraying what's actually happening in the field. My rate is also very, very important. So who knows? Maybe if you basically tested at low temperature, very, very low temperature, sorry, -12 degrees Celsius at a very slow loading rate, right, which would simulate kind of higher temperature, you would get similar results to our 25 degrees Celsius. So what we're doing here is we're not taking anything for granted, basically. We're not assuming that the current classic SCV testing setup is accurate. We're also examining that, which is kind of why I'm saying it wouldn't necessarily be the thing to basically compare to. You see what I'm saying? You get a question?
It was the same as Rebecca's.
Okay.
Telling me right, yeah.
Okay.